Nat 4-5 Physics, Acceleration. The key areas we will cover today are calculating acceleration from velocity time graphs and some review questions. The review questions will incorporate both graph-based questions and written questions where you have to take the values from the sentences. Calculating acceleration from graphs. Acceleration can be calculated from any speed or velocity time graph. We have three graphs here that we looked at in a previous lesson, and what we can do is work out the acceleration from each of these graphs. Instead of calculating the area under the graph, as that's equal to the distance, what we want to do is take the values from the graph. So the initial speed, the final speed, and the time. This will allow us to calculate acceleration using our acceleration equation. First, let's look at graph A. All horizontal lines on speed-time graphs give an acceleration of 0 meters per second squared. The gradient of a horizontal line is always 0. Let's prove this for this graph. Our acceleration is what we want to calculate. We need our initial speed, our final speed, and our time. Looking at the graph, the initial speed is 4 meters per second. And looking at the graph again, our final speed at the end of the line is again 4 meters per second. This happens in a time of 15 seconds. Using our equation, A equals v take away u divided by t, we can see our acceleration equals 4 take away 4 divided by 15. Therefore, our acceleration equals 0 divided by 15, and 0 divided by any number is always 0. So our acceleration is 0 meters per second squared, which is exactly what we were calculating before, so we know the acceleration on this graph is 0. There hasn't been any increase or decrease in speed. The speed has stayed the same. Graph B. All upward sloping lines on a speed or velocity time graph give a positive value from an acceleration calculation. The gradient of an upward sloping line is always a positive value, and what we want to do is show that the gradient of the line in graph B is 0.4. To do this, we want to show that the acceleration is 0.4, as the gradient and the acceleration are the same. So we want to work out the acceleration. We need our initial speed, we need our final speed, and we need our time. Looking at the graph, right at the start, we can see that the initial speed is 0 meters per second. Again, looking at the graph, our final speed up here, if we follow a dotted line across, we can see that it's 6 meters per second. And finally, we can see this happens in a time of 15 seconds again. Using our equation, A equals v take away u over t, we can pop our values in. So A equals 6 take away 0 divided by 15. 6 take away 0 is just 6, so we can simplify our equation to be A equals 6 divided by 15. And 6 divided by 15 does give us an answer of 0.4. And that's meters per second squared if it's an acceleration, and that's the same as the gradient, which is 0.4 there. That's our final answer. Graph C. All downward sloping lines on a speed or velocity time graph give a negative value from an acceleration calculation. The gradient of a downward sloping line is always a negative value. This time, we need to show that the gradient of the line in graph C is negative 0.27. So again, we're calculating the acceleration, and this is the number we should get. So our acceleration is where we want our question mark. Our initial speed, our final speed, and our time are what we need to get from the graph. So looking at the graph, our initial speed at the top of the line is this 4 meters per second. And our final speed is at the bottom of the line down here, which we can see to be 0 meters per second. And we also have a time, again, just like the last two graphs, of 15 seconds. Now we want to write our equation. A equals v take away u divided by t. Popping in our numbers, we get our acceleration is equal to 0 take away 4 divided by 15. And just like previously, we need to take into account that there's a negative sign there. We can't just get rid of the negative, we need to keep it. So simplifying the top row of the equation, we get acceleration equals negative 4 divided by 15. Negative 4 divided by 15 does give us 0.27. Initially what comes out the calculator is a equals negative 0.2666. It just keeps on going with sixes, so we want to round this number, and if we round it to two significant figures we get negative 0.27 meters per second squared. So because our acceleration is negative 0.27 meters per second squared, that is indeed showing that the gradient of the graph is negative 0.27. Again, you can see this negative means a deceleration, and that's our downward sloping line on the graph. It's a negative gradient, so a negative acceleration. It can be shown that for all speed or velocity time graphs that a equals the gradient of the line on this velocity time graph, so the acceleration equals the gradient of the line. Here are some review questions that you can try. The answers will be on the next slide, but after that there will be full working for each of the questions, so if you get any wrong you can go through and have a look where you went wrong. Pause now if you would like to have a go at these questions. Here are the review answers if you were completing the questions by yourself first. If any of your answers are wrong, have a look at the working on the next few slides for that specific question and see where you went wrong. Let's look at some review questions. Question 1. A graph showing how the speed of a tennis ball changes whilst in contact with a racket during a serve is shown below. Calculate the acceleration of the ball during the serve. So we need to use our acceleration calculation and this graph to calculate the acceleration of the ball. So we need a question mark next to our A. We need our initial speed, our final speed, and our time. Our initial speed, looking at the graph, we can see it starts off at a time of 0, it has 0 meters per second of speed. Looking at the graph again, our final speed is going to be up here, and there are some convenient dotted lines for us to look at. Our initial speed is 50, and again that's in meters per second because it tells us on the axes just here. Looking at our time, that's a difference between 0 and 0.004, so our time is 0.004 seconds. Now we can use our equation, A equals v take away u over t. Pop in our numbers, our acceleration equals 50 take away 0 divided by 0.004. We can simplify this for ourselves to say that acceleration equals 50 over 0.004, and this is going to be equal to 12,500. And remember your units, that's meters per second squared. Question 2. The speed of a go-kart is recorded from the start of a race for the first 4 seconds. The go-kart is travelling at 12 meters per second after 4 seconds. Calculate the acceleration of the go-kart. So this time we're not using a graph, it's just a plain acceleration equation calculation. So we want to calculate the acceleration. We need our initial speed, final speed, and time to do that. So having a look at the question, our initial speed, well, it's not telling us an exact number. However, the speed of the go-kart is recorded from the start of the race. What can we determine happens at the start of the race? The go-kart starts at 0 meters per second. Just like when we say from rest, if we're presuming it's the start of the race, then the go-kart mustn't be moving. It will start moving when the race begins. So we can put that into our numbers at the left. So our initial speed is 0 meters per second. And we can see this is for the first 4 seconds the speed is recorded, so that's going to be our time. And the go-kart is travelling at 12 meters per second after this 4 seconds, so that's our final speed. Using our equation, A equals v take away u over t, we can pop our numbers in. So A equals 12 take away 0 divided by 4. Simplifying this, we get A equals 12 over 4, so our acceleration is 3 meters per second. Oh, did you see my mistake there? Not 3 meters per second, that would be its speed. 3 meters per second squared, because it's an acceleration. It's the change in speed per unit time. Question 3. A jet achieves its minimum takeoff speed by accelerating from rest at 35 meters per second squared for 2 seconds. Calculate the minimum takeoff speed of the jet. As always, we want to write down our values on the left-hand side. Our acceleration is mentioned in the question this time. That's that 35 meters per second squared. With questions like this, it can sometimes be confusing which values we're putting down for each letter. What you need to do is take notice of the units that they're measured in. Because this 35 is meters per second squared, the only value it could be written down as is the acceleration. Next, we want our initial speed. In the question, we can see that the jet is achieving its minimum takeoff speed by accelerating from rest. Again, there's that phrase coming up. From rest means it's starting at 0 meters per second. So our initial speed, 0 meters per second. Our final speed is what it wants us to calculate, because it says calculate the minimum takeoff speed of the jet. So that's where our question mark goes. And finally, our time, we can see it just there, it's 2 seconds. Using our equation, A equals V take away U divided by T, we can pop in our numbers. So 35 equals V take away 0 over 2. Simplifying this, we notice that V take away 0 is just V, so 35 equals V over 2. Rearrange this and we get our final speed equals 35 times by 2, which equals 70 meters per second because it's a speed. So that's the minimum takeoff speed for the jet, 70 meters per second. Question 4. An athlete changes their speed from 3 meters per second to 14 meters per second by accelerating at 5 meters per second squared. Calculate the time taken to make this change in their speed. We can see it says calculate the time taken here, so that's where we want a question mark this time. And we can also see they're changing their speed from 3 meters per second to 14 meters per second. So the initial speed is 3, and the final speed is 14, both in meters per second. And finally, our acceleration is 5 meters per second squared. We can use our equation to calculate the time. So A equals V take away U divided by T. Let's put in our numbers. So 5 equals 14 take away 3 divided by T. Let's simplify it for ourselves. So 14 take away 3 is equal to 11. So 5 equals 11 divided by our time. Let's rearrange this, take our time up to the other side, so 5 times by our time equals 11, and take our 5 back down to the other side, so time equals 11 divided by 5. 11 divided by 5 is equal to 2.2, so that's our final time. That's 2.2 seconds. Always remember your units. Question 5. A graph of a cyclist's motion during a race is shown below. Part A. State the time when they start travelling at a constant speed. And Part B. Calculate the acceleration of the cyclist. First of all, we want to look at this graph and state the time when they are travelling at a constant speed. We have two different shapes of graph in here, and the first one is a positive gradient, and we know that a positive gradient, just here, is an acceleration. So the cyclist is not travelling at constant speed here, their speed is increasing, they are accelerating. The flat part of the graph just here is where the cyclist is travelling at a constant speed, their speed is not changing. So it's this point just here where they stop accelerating and they start travelling at a constant speed that we want to know the time of. So if we draw a dotted line down to the time axis, we can see this corresponds to a time of 15 seconds. Let's look at part B now. We want to calculate the acceleration of the cyclist. So using our equation, we want to first write down our values. So A is our question mark. We need our initial speed, our final speed, and our time. Because we're calculating specifically the acceleration of the cyclist, we just want to look at the part of the graph which has a positive gradient, so between 0 and 15 seconds. Our initial speed is 0, because the cyclist starts at this 0 point down here. And our final speed, we want to look at this point where I've got the arrow again, but follow its left this time, to our y-axis. We can see this corresponds to a speed of 18 meters per second. And this all happens in a time of 15 seconds, like I mentioned. Now we want to use our equation. A equals V take away U divided by T, and pop in our numbers. So A equals 18 take away 0 divided by 15. We can simplify this for ourselves, saying that our acceleration is equal to 18 over 15, and 18 divided by 15 is equal to 1.2. So the acceleration of the cyclist is 1.2 meters per second squared.